All right, everyone, we had some homework over the weekend, worksheet number 12. Let's take a look at the answers to worksheet number 12. Again, don't worry about the solutions right now. If you have trouble with any of them, or if you didn't get the answer to one of them, then just focus on that and then ask me when we're ready to go over them here, okay? Number 1 to 4, number 1 to 3, sorry. 1 to 3. See if we can get all those up together there. Yeah. You have a peek. And let's take a look at 4 and 5. Number 5, the number got cut off. It should have been, oh, it's cut off on my sheet as well. Looks like something like, I don't know, something point something times 10 to the minus 4. How does that work out to be? Does anybody have that? It's cut off on my original sheet here too, guys, so I can't tell you what the answer is right now. I'll probably nobody did get that. That was a tough one, wasn't it? Yeah. Okay, so we'll definitely go over number 5. Definitely go over number 5. Any others that you need to go over, 1 through 4? Yep. 4 and 5? All right, 4 and 5 it is. All right, number 4 says, what's the kinetic energy in joules and electron volts of an alpha particle? I circled, you can see that when I did my answer key, I circled alpha particle. Why would I have done that? Yeah, I don't need to circle right now because I've already done it, but why would I have done that when I did my answer key in the first place, Liam? It's a positive particle, and it's got a charge of 3.2 times 10 to the minus 19 coulombs. Now, that doesn't make it harder than dealing with an electron that's a negative charge, or 1.6 times 10 to the minus 19, but it's different. We're so used to dealing with electrons that when I see something that's different than an electron, I like to draw attention to it. I even, to be honest, if it's an electron, I often circle it in red or underline it or something, just to draw attention to it. There's so many different particles, there's so many different charges, protons, alpha particles, electrons, certain types of ions, other particles that we'll see in our last unit, that it's easy to just use one charge instead of the other one, instead of the right one. So let's draw attention to that. We know what the charge is, we know what the mass is. That is, if we look on our data sheet, moves through a magnetic field of strength 1.0 times 10 to the minus 1 Tesla, that's B, follows a circular path of this radius. We're looking for kinetic energy. That's a little bit different. Okay, we haven't solved a problem yet involving magnetic fields where we're looking for kinetic energy. That's okay. Okay, we know what to do when we see a question with a charged particle moving through a magnetic field. We don't need to worry about it being a little bit different than problems that we've seen. Okay, just attack it like we attack all of them. We know that we have 3 equations that are valid every single time a charged particle goes through a magnetic field. There's this one. There's the one that we learned first. F is equal to QVB. And then, of course, we've got FC is equal to mv squared over r, because the charged particle goes in a circle as it goes through the magnetic field. But then, of course, we've got FC is equal to FM, the combination of these 2 equations. Which one did I say you're usually going to use if you're dealing with a radius? The combination of them. Somebody said both. Yeah, the combination of them. FC is equal to FM. There's no guarantees. Okay, we might end up trying this and finding we have 2 or 3 unknowns, and then we have to try something else, and that's okay. Don't panic about that. But try this first, because you're not going to go wrong with it, and odds are you're going to go right with it. So let's try this. mv squared over r is equal to qvb. We know that one of the v's cancels on both sides. So we're left with mv over r is equal to q times b. Now, I don't see kinetic energy in there anywhere. Let's see what exactly we can solve for here. We know what m is. We don't know what v is. We know what r is. We know what q is. We know what b is. That allows us to solve for v. Even though it's not what we're looking for, it's more than we've got right now, which is usually a positive thing. So let's solve for v. Take the r up by multiplying. It becomes q times b times r. And then we're going to take the m down by dividing. Q, B, R over M. Let's see what we get for that. Look, I almost went 1.6 times 10 to the minus 19 for the charge. But I've got an alpha particle here, and I've got it circled to remind me that it's an alpha particle. So we're going to say it's 3.2 times 10 to the minus 19 coulombs. Times a magnetic field of 1 times 10 to the negative 1, is that? Yep. That's going to be 0.10 times a radius of 0.025. Divided by the mass, again on your data sheet, 6.65 times 10 to the minus 27 kilograms. Let's solve for that speed. When we do, we get 120,300.75 meters per second. That's a speed 10 to the 5, 1.2 times 10 to the 5 meters per second. Reasonable speed for a charged particle? Yeah, usually it's 10 to the 5, 10 to the 6. Could be different, but usually in that range. All right, so we've got a speed. It's not what we're looking for. Is it helpful? Worst case scenario is no, it's not helpful. And we got to try something else. That's the worst case scenario here. Best case scenario, it's going to help us to get the answer for kinetic energy. What are you going to do at this point? You're going to use this, or are you going to abandon this method and try something else? Let's use it, yeah? How are we going to use it there, Mac? Right. Now that we've got speed and the mass, of course, let's use EK is equal to 1/2 mv squared. Some of you may have kind of worked the other way. Some of you may have said, oh, wait, I want to find kinetic energy. I've got to use 1/2 mv squared. All right, how am I going to get V? Okay, sometimes I look at it that way. Okay, in this particular case, the first thing that I thought of was not EK is equal to 1 mv squared. First thing I thought of was this. And then I solved for V, and then I realized, oh, okay, now I'm going to use 1/2 mv squared. So it's use a number for the mass of the alpha particle that's on our data sheet, the speed that we just got. And when we solve for that, we get 4.8 times 10 to the minus 17 joules. Now, just looking at my answer sheet here, I didn't calculate the energy in electron volts. I just did joules. This is what it is in joules. Okay, so let's get it in electron volts now. How exactly do we do that conversion of joules to electron volts? I'm sorry? Yeah, set up a ratio. 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. And where do we get that ratio from right there? 1 to 1.6. Where does that come from? Travis? Well, no, 1 electron volt is equal to this many joules, so it's an energy to an energy. But where does that come from? It's our data sheet, right? On the left-hand side of our data sheet, it tells us an electron volt is equal to 1.6 times 10 to the minus 19 joules. All right, that's equal to X electron volts over 4.8 times 10 to the minus 17 joules. Solve for X, the 4.8 goes up, then we divide 4.8 by 1.6, and we're going to get, I don't have the answer on my sheet, but I think that works out to be 200. No, sorry, yeah, 300. So 3.0 times 10 to the 2 electron volts. Anybody get, how many people got the answer in both joules and electron volts correct? Okay. Good. All right, and finally, question number 5. Honestly, I didn't anticipate very many people would get question number 5 correct, if anybody. That's okay. Hey, this was meant as probably as much as a teaching question as it was a practice evaluation question. I knew we'd have to go over this question. How does the radius of curvature of an electron, shouldn't say of an electron, it should say an electron's path, right? Because we're not talking about the radius of an electron itself. We're talking about the radius of the path of the electron. Okay, I think you guys knew what I meant on that question, though. Compared to the radius of the curvature of the alpha particle's path, moving through the same magnetic field at the same speed. All right, let's assume for a second that I'm 36. I'm not quite 36, but not that far off. And let's assume that you guys are 18. I know that some of you guys are and some of you aren't. What's the ratio of my age to your age? 2 to 1, right. How'd you get that? Yeah, 18 is half of 36. 36 divided by 18 is 2. So the ratio is 2 to 1. What's the ratio of your age to my age? 1 to 2. Okay. So how do we get that? Well, we divided 18 by 36, and we got a half, so the ratio is 1 to 2. So when we want to find a ratio between two things, then we're going to divide them, right? The ratio of A to B is A divided by B. The ratio of B to A is B divided by A. If we want to find the ratio, or we want to compare the radius of curvature of the alpha particle's path, the electron's path to the alpha particle's path, then let's divide the radius of the electron's path by the radius of the alpha particle's path, just like we divided my h d or h. Pretty soon it's gonna, this little analogy that I use is, I'm gonna have to switch from pretending I'm 36 to pretending I'm, no, it's a while before I'm 54. It's a long time before I'm 54. At some point that's gonna happen though. All right, so how do we divide those two numbers? We don't know what the radius is, right? We don't know what the radius is. If we knew what the numbers were, easy, right? 36 divided by 18, 2. Easy calculation when we know what the numbers are to plug in there. In this case, we don't, though. So let's get an equation for the radius of the path of the alpha particle and the electron. We know that Fc is equal to Fm. So we say mv squared over r is equal to qvb. One of the v's disappears. Let's solve for r. The r goes up by multiplying. The qb goes down by dividing. And it becomes mv over qb. Is that good? Everybody okay with that? So basically cross multiplied, r goes up, qb goes down. All right, the radius of the electron's path would be m electron, speed electron, over the charge of the electron, divided by the magnetic field experienced by the electron. The radius of the alpha particle's path would be the mass of the alpha particle times the speed of the alpha particle over the charge of the alpha particle, divided by the magnetic field experienced by the alpha particle. But in this question, they tell me that it's the same magnetic field. So the magnetic field experienced by the alpha particle, right, is the same as the magnetic field experienced by the electron. They cancel because it's the same value. Same thing for the speed. The speed of the electron and the speed of the alpha particle are the same, so we can cancel. Now, if we want to find the ratio of these two, I can plug in our numbers here. Okay, we know what ME is. It's 9.11 times 10 to the minus 31. Divided by 1.6 times 10 to the minus 19 coulombs. Divide that by 6.65, the mass of the alpha particle, over 3.2 times 10 to the minus 19 coulombs. So let's get a number on the top. Okay, let's get a number on the bottom. And when we do that, let's see what we get here, okay? Let's pull out the calculator and see what we get, since my answer didn't show up on my answer sheet. Let's say 9.11 times 10 to the minus 31, divided by 1.6 times 10 to the minus 19. Let's get that number, and then let's divide that by, use some brackets, 6.65 times 10 to the minus 27, and divide that again by 3.2 times 10 to the minus 19. That gives us 2.7 times 10 to the negative 4. What's the ratio? 2.7 times 10 to the minus 4 to 1. Right? 36 divided by 18 gives us a ratio of 2 to 1. Okay? This divided by that gives us a ratio of 2.7 times 10 to the minus 4 to 1. It's a uglier looking ratio for sure, right? We're not as comfortable with seeing numbers like that as we are a ratio of 2 to 1. Okay? But it is what it is. It's the same thing. It's just numbers that are a little bit less pretty, that's all. Did anybody happen to get that number? No? Okay, that's okay. Paige? Okay, fair enough. We're talking about a comparison here, guys. And the reality is, I mean, we can compare in a number of different ways, right? We can compare by dividing and getting a ratio like that. We can compare by subtracting. We can compare by all kinds of all kinds of different ways. But the best way of comparing numerically, I mean, if you got qualitatively comparing, hey, let's compare the color of Warren's shirt to Colton's jacket. Well, it's kind of pinkish to blue. Okay, well, we can't divide there, right? But if we're comparing numerically, the best way to compare is divide. We can subtract. Okay? There's a 2-year-old and a 1-year-old, let's say. Okay? Obviously, we know that a 2-year-old is quite a bit more advanced than a 1-year-old child, right? Well, how do we compare the two? Well, we say there's 1 year difference, right? Is that a valid comparison? Sure it is. What's a better comparison? To say the 2-year-old is twice as old as the 1-year-old. That expresses that age a lot better by dividing, right, than it does by subtracting. Why? Because later on in their lives, when one of them is 47 and one of them is 48, we compare them. If we subtract them, there's still 1 year difference. But there's a lot less difference between them than when they were 2 and 1, right? If we divide and say, oh, look, this guy's twice as old as this guy, well, you can tell there's going to be a big difference in those people, right? But if we subtract them, look, there's 1 year difference, whether they're 1 and 2 or 47 and 48. So let's divide. Whenever we're asked to compare two things numerically like this, let's divide instead of subtract. Okay, that's what the diploma exam is always going to expect us to do, is to divide those two numbers. All right. All right, let's take a step forward here now and well, in a sense, take a step forward. In a sense, take a step backwards. Start talking about electric current. Just briefly, though. Why electric current now? We finished our electricity unit a while ago. We're doing our magnetism unit. Now, all of a sudden, we're going back to defining electric current, which is a purely electrical phenomenon. You'll see in a minute. Trust me, you'll see in a minute. The good news is we don't get very deeply into electric current, and it's easy. Electric current is simply defined as the rate of flow of electric charge, not the speed of electric charge, okay, not how fast electric charge is moving. If I'm standing on the side of the highway with a radar gun, that's going to measure the speed of the cars going by. If I'm standing on the side of the road counting the number of cars going by and timing it with a stopwatch, look, there's 6 cars per second flying by me. That's analogous to current. So the radar gun is analogous to the speed of the charges. Counting the number of cars that are going by per second is analogous to the electric current. It's the rate of flow of charge, how much charge flows per second, not how far the charge goes per second. The symbol for electric current is I, a capital I. Sometimes you'll see it as a lowercase I, but not in Physics 30. If you take a university course in physics, they may call it a lowercase I. Okay, but in Physics 30, including on the diploma exam, it will always be a capital I. Q means what? Charge. And T means time. Now, you can see below here that the unit for electric charge is the ampere, or the amp. The plug-in in the back of the room is a 15 amp circuit. 15 amps, the electric current that plug-in can draw. Sometimes you get a plug-in that's 20 amps. Okay? You can draw 20 amps. If you ever see, by the way, in your house, a plug-in that has the 3 prongs, 2 verticals, it looks like this, kind of looks like a face almost. That's a 15 amp, means it can draw 15 amps. If you see a plug-in that's like this, which you can still plug your regular things into, but it's got a little horizontal thing like this, that means it can draw 20 amps. This means the circuit breaker will allow it to draw more current, that's all. Okay, so amps, amperes is electric current. What are the other units that you can see from the equation that electric current could be measured in? Coulombs per second. And a coulomb per second is exactly the same thing as an amp. So whatever you see, just use it, whatever you're more comfortable with. Okay, be prepared to see both of them. All right, quick little example problem with that. And again, right now, you're still probably wondering, well, why are we doing this right now? Why are we doing charge and time again when we're doing magnetism? That's the unit. You'll see in just a moment here after we finish these easy sample problems here. It says calculate the current in a wire through which 20 coulombs of charge passes through in 4 seconds. Okay, really, really easy question, I hope. We're going to say I is equal to Q over T. I get 20 coulombs divided by 4.00 seconds gives me 5 amps, or 5.00 coulombs per second. Right? Easy enough, right? Give you a couple quick little samples of this that I want you to work on just to make sure that it's okay. And then we'll go forward that next step, which is going to explain to you why we're talking about this right now. Okay, see what you can do with these ones, guys. I'll give you about a minute or a minute and a half to do this. All right, if there's no problems with those two questions, let's go a step forward now. Now you're going to see why we're talking about electric current. In the end, guys, it all relates to magnetic fields, right? Magnetic forces. A charged particle moving through a magnetic field, you guys learned this last week. A charged particle moving through a magnetic field, just moving through the air, will generate its own magnetic field, which will interact with the external magnetic field that was already there to produce a force on that moving charge. That force will cause the moving charge to deflect. Okay, it's going to experience a force perpendicular to the field, perpendicular to the way the particle is moving, and that particle is going to deflect in that direction of that force. Now, if we have a charge that's moving through the air, that applies. If we have a charge that's moving through a wire, that also applies. But when we have a charge that's moving through the wire, we usually call it what? Electric current. That's a current when a charge moves through a wire. So today we're going to learn how to analyze specifically electric charges moving through a wire when they're exposed to an external magnetic field. It's really the same thing as we did last week, but the equation looks slightly different because we're going to relate the force not to the charge that's going through, but rather the charge per second that's going through. In other words, we're going to relate the force to the electric current. Okay, so a current-carrying wire simply consists of moving electrons inside a conductor. Okay, it's the same thing as it was before, but now it's in a wire. Because of that, because it's the same thing, those electrons will experience a magnetic force. Now, if the electrons experience a magnetic force, then the wire itself will experience a magnetic force as well. These particles won't go in a circle. When they're moving through the air, they always go in a circular path, right? When they're going through a wire, they want to go in a circular path, but they can't because they're held in a line by the wire itself. So the wire will experience a force, but we can't use the centripetal force equation here because it doesn't go in a circle. Now we can find the direction of the magnetic force in exactly the same way as we found it before with just moving charges through the air. Because again, all we have is moving charges here, except this time it's through a wire. We're going to look at the direction of the particle motion, which is the direction of the electric current. In this case, as you see it on the board here, that particle is going into the board. The external magnetic field is going from north to south. So we're going to say thumb in the direction of the particle, fingers from north to south, palm is going to point toward the top of the page. It's no different, right? We're still going to call it the hand rule for deflection. It's the same rule. We're just thinking of it slightly differently this time. It was put your thumb in the direction the particle is moving, fingers field, palm force. Now it's put your thumb in the direction of the current, fingers field, palm force. But really, it's the same thing because the direction the particle is moving is the direction of the current. So if your thumb goes in the direction of the moving charge, your fingers, which are straight this time, right, not bent, straight, are in the direction of the external magnetic field. It's the magnetic field caused by the magnets or caused by the earth or caused by whatever. And your palm will automatically point in the direction of the magnetic force. Now, all of this assumes what? For this rule to be valid, then what has to be the case? It has to be perpendicular. The charged particle's got to be moving perpendicular to the field. In other words, the wire has to be perpendicular to the field. If that's not the case, that rule doesn't apply. If they're parallel, what's the force? 0. If they're not perpendicular or parallel, what's the force? We don't know. We don't really care. Okay, that's for another day. What about the value of the force, the magnitude of the force? We know the direction now. Wire, it's the hand rule for deflection. The magnitude can be found by an equation that looks different, okay, than the other equation we used, F is equal to QVB, but in the end is derived from that equation. We won't go through that derivation, but here's the final product. The magnetic force, okay, magnetic force measured in newtons is equal to what? I times L times B. I stands for the current, right? We learned what current was just a few minutes ago. Current is equal to Q over T, the charge over the time. Sometimes in a question like this, maybe you're given the current. You don't need to worry about the fact that it's Q over T. Sometimes you might need to find it by dividing Q by T and then plugging it into here. The current, which is measured in coulombs per second or amps. What does L stand for? The length of what? Good, the length of the wire. Specifically, the length of the wire exposed to the field. So in other words, if you've got a 20 centimeter long wire, but only 15 centimeters of it is in the magnetic field and 5 centimeters is outside of the magnetic field, then the length that we care about is 15, right? The length that we care about is the 15 centimeters because that's what's exposed to the magnetic field. That is, if it's perpendicular. If you've got a situation like this, here's a good question. Here's a great question, actually. Here's a wire carrying an electric current going clockwise. Okay, let's put some dimensions in here. Let's make this 5 centimeters. Let's make this 5 centimeters. And let's make this 6 centimeters. What would be the length of the wire in this case? No, not 6. What would be the length of the wire in this case? Not 20. Not 16. Who said 10? David? Why is it 10, David? We care about this, and we care about this. We don't care about this because it's not exposed to the magnetic field. Okay? That's actually not a great diagram because there is a magnetic field down there, right? Okay? Let's assume that there was just the magnetic field in between the north and the south. Okay? Then we wouldn't care about what was down there, not exposed to the magnetic field. We don't care about the 6 centimeters. Why not? Because it's parallel. So the only thing we'd care about here would be this 5 and this 5, meaning the length of the wire would be 10 centimeters or 0.1 meters. Make sense? We only care about the part that's parallel to, perpendicular to the magnetic field and the part that's in the magnetic field itself. B stands for, that's the magnetic field strength, right? And that's going to be measured in Tesla. What's that little upside down T thing mean? We talked about that with our last equation, right? Perpendicular, right? This equation only applies when the wire is perpendicular to the magnetic field. This doesn't sound too hard. It isn't, right? In fact, it's arguably easier than a charged particle moving through the air in a magnetic field because we don't have to worry about the circular part of this because it's not going to go in a circle. Right? It can't go in a circle because the particles are inside the wire and the wire doesn't let it go in a circle. Yeah. Yes, yes, good question. I should have wrote that down. Length is always measured in meters, yes. Everything we do, length will be measured in meters. Okay, here's an example. An 8.5 centimeter long length of wire. Okay, Dallin's question leads really well into this question because we see our length in centimeters and we want it in meters. It's perpendicular to an external magnetic field of 4.20 millitesla. We don't like those units either. There's a negative charge flow of 2.1 amps in the conductor. Calculate the magnitude and determine the direction of the magnetic force. All right, so let's make this L. Let's make this B. Let's make this I. We're looking for F. Hey, what if this? No, I'll ask that question later on. I'll ask that later on. Want to find the magnitude of the force we're simply going to say it's I times L times B. So we're going to say 2.1 amps times a length here of 0.085 meters. And 8.5 times 10 to the minus 2, or 8.5 divided by 100, 0.085. Millitesla is 10 to the minus 3 Tesla. Let's multiply those three numbers together. And we get 7.49, 7.50 times 10 to the minus 4 newtons. So how do we go about finding the direction of the magnetic force on this wire? And rule for deflection, right? Thumb, everybody take your left hand out here, guys. Okay, it's a negative particle, so it's left hand. Thumb in the direction of the particle into the page. Fingers, magnetic field is going from north to south, so fingers are going from north to south to the right. Palm points upwards towards the top of the page, right? Now, how would this question change if it said a conventional current of 2.10 amps? You guys remember that term? Okay, we talked about that briefly one day and said, I think in all the years that I've done this, I've only seen that on a diploma exam maybe a couple of times. Conventional current, but just in case. Okay, conventional current means positive, use your right hand, right? Okay, we doubt that that's going to happen to us, but we want to be ready for it just in case. We hate to lose a mark on this question just because of that, right? Yeah, go ahead, Travis. All right, see what you can do with these two questions here. And then we'll move forward a little bit. All right, let's take a look at number 2. It says a thin conducting wire, 0.75 meters long, has a mass of 0.060 kilograms. What's the minimum current required to make it float? How's it going to float? How's a wire going to float in this magnetic field? I'm sorry? Okay, so it's not moving. What do you know if something's not moving? What must be the case? Good. When something's not moving, forces have to balance. If there's any forces at all, they've got to balance. Now, in this case, we've got a magnetic force. And Mac correctly said that magnetic force has to balance something. In this case, what balances the force of gravity. If something's floating, if something's suspended, okay, it's going to go Fm is equal to Fg, or Fe is equal to Fg, or F something is equal to Fg. Something's probably going to balance gravity if something's floating or suspended. So we're going to say ILB here is equal to M times G, and we're looking for the current there. We're looking for I. So I becomes equal to mg over L times B. Notice I'm making the L a capital L. Okay, in your equation on your data sheet, it's actually a lowercase l. But look what my lowercase l looks like when I print it. Looks like a 1, right? So that's why I'm making it a capital L. Okay, on your data sheet, it's lowercase. I'm making it a capital just so you can tell I don't mean 1. Right? We know the mass here. Now this question is pretty straightforward. 0.060 times 9.81 divided by the length of 0.75 times 0.15. And when we do that, I think we should get 5.2 amps. Good? Yes? Take a look at this, guys. This is another application of things that we're doing here. Okay, it's not the electrostatic painting on the fence, or it's not the electric fire alarm or doorbell or whatever. This is an electric motor. And we said way back when we started this unit, Josh, that one of the most important technological discoveries ever made was Ørsted's discovery in 1819 that electric current generates a magnetic field. We said that's in just about every bit of technology, certainly electronic technology, that we have today. Electric motors are used everywhere, literally from little toy cars to inside your phone. It's what makes your phone vibrate, is a little electric motor that's got a weight off balance, so that when it rotates, it makes it vibrate a little bit. The electric motors are used just about everywhere. So how do they work? What do they do, first of all? An electric current makes something turn. That's it. An electric current makes something turn. Makes the wheels of a toy car turn. Okay, it makes the armature of a little motor inside your cell phone to make it vibrate. It turns. Just got a weight that's off center that makes it vibrate. Okay, it makes the fan in your hairdryer turn, or the fan in your ceiling turn, okay, in your ceiling in your bedroom, or whatever. Okay, it's an electric current that makes something turn. So how does it work? Well, here's a basic diagram of an electric motor. Okay, the reality is if you saw a real electric motor inside something, it would be a little bit more complicated than this because you'd have more wire and you want to make it stronger and so on. But the basic idea is this. We have two magnets. Okay, two magnets. These are permanent magnets with a north pole and a south pole. They would continue, of course. There'd be a north pole down there. We just don't need to see that. Because of that, we have a magnetic field going this way, from north to south. Now, we have a battery down here as a negative end and a positive end. That will cause the electric current to flow this way. That electric current flows clockwise there, and it reaches this little black thing that we call a brush. That brush is attached to the wire, but not attached to this thing that we're calling the armature, this thing right here. Not attached to this thing that we call the commutator. It's touching it, but it's not attached to it. So this round thing right here that you see called the commutator is free to turn. The brushes don't. The brushes stay where they are. The commutator can turn, but it's touching. So the electrons, as it's touching, will go from the wire through this brush, through the commutator, and then around this armature like this, clockwise, to the brush on the other side, okay, through the commutator, and then back around. Make sense? We get a complete circuit flowing here. Now, as we get that complete circuit flowing, notice we have a charged particle or a wire that carries an electric current in an external magnetic field. That causes a force. In fact, there's two of them here. Let's look at the force right here. Let's say 1, 2, 3, 4. The force on section 1, 2. Particles going this way, palm or fingers go this way, palm points kind of upwards. So there's a magnetic force acting on this wire that's upwards. Let's look at the other side. Thumb goes out of the page, fingers from north to south, palm points downward. There's a force on it acting downward. What happens to this armature? It turns, it rotates, right? It's what we call a torque. A torque is an off-center force. When you have an off-center force, something rotates. This door has a pivot point right over there at the hinges. If I apply a force off-center, then I'm applying a torque to the door. And then what's the result of a torque? It turns, it rotates. The further from the pivot point, the more the torque. Okay, that's why when you push the door right here, it doesn't turn very well. When you push it out here, it turns pretty easily, right? That's why when you're trying to take a really tight bolt off of the wheel, or sorry, a really tight wheel nut, wheel lug off of your wheel, you can't get it turning, right? What do? You get a longer wrench. You get a longer wrench so you can be further from the pivot point. Okay, it's more torque. Okay, it causes rotation easier in that case. Make sense? So there's a torque on this which causes it to rotate. All right, when it rotates a quarter of a revolution, however, 1/4 of a revolution, this little thing in the middle here, this little gap that you see, which is not a conductor, is now in contact with the brushes. Now what happens to the electric current? When this gap, which is an insulator, is in contact with the brushes, the electric current stops. So now what you've got is this armature started like this. it turns 90 degrees. There's no electric current going through there, so there's now no electric force, right? But it keeps turning a little bit because of inertia, rotational inertia. It keeps spinning just because it was already moving and it wants to keep doing what it was doing. So it does. It keeps turning a little bit on its own. The magnetic force causes it to do this. Inertia causes it to keep going a little bit. Now what I want you to do, I'm going to label this piece of paper actually that I have in my hand here. The same way as I have that labeled on the board there. Okay, there's my wire. 1, 2, 3, 4. See that? Turns 1/4 of a revolution. Now it goes a little bit beyond that, and you can see now that the wire is set up so that it's 4, 3, 2, 1. Okay, when the wire is turned like this, it becomes 4, 3, 2, 1. Does that make sense? Okay, when the wire flips over, 1 and 2 goes over to the other side, 3 and 4 goes over to the other side, so now that's the orientation of it. The current is now reversed in this wire. That's the purpose of this thing that we call the split ring commutator. It reverses the current in the wire. It still goes clockwise, but instead of going 1, 2, 3, 4, now it's going from clockwise 4, 3, 2, 1. Does that make sense? The current's reversed in the wire, but it does that so that the magnetic force still points upward on the left side and downward on the right side. So that causes another 1/4 of a turn. Went like this, 1/4 of a turn, kept going a little bit because of inertia, goes another 1/4 of a turn because of this magnetic force. Now the magnetic force is broken again. Okay, it keeps going a little bit by inertia, makes another 1/4 of a turn, and so on and so on and so on, so that this thing keeps just rotating. All right? That's your electric motor. Attached on the end of that armature might be a drill bit, if it's your electric drill. It might be fan on your ceiling attached to the end of the armature. It might be the bristles on your electric toothbrush that's attached to the end of that armature. It might be that little weight, that little mass that's off center in your cell phone, the motor in your cell phone that causes the vibration. Whatever it is that spins is attached to that armature. Now, how could we make this thing spin faster? There's 3 ways that I can think of to make it spin faster. What's one of them? Increase the current going through it, right? If you have more current, a stronger battery, more current going through it, it's going to spin faster, right? That's what happens when you have a variable speed drill, which most drills are now. Okay, pull the trigger, pull it further, it goes faster, right? What are you doing? You're allowing more electric current to go through it when you do that. Okay, when you have a mix master and you're trying to, mix the cake batter, you flip it from speed 1 to speed 2 to speed 3 to speed 4, and you make it go faster and faster and faster. When you're doing that, you're allowing more electric current to go through it with each consecutive speed there. What's another way? Increase the magnetic field, all right? Increase the magnetic field strength. Stronger magnets, right? Finally, what's the third way? Increase the length of the wire. Okay. Bottom line is, how do you make this thing go faster? Increase the magnetic force. How do you increase the magnetic force? Increase I, increase L, increase B. Got it? Now, how would you increase the length of the wire? What you'd probably do is do this. You just have loops of wire going through there. This part of it right here doesn't matter. This part of it doesn't matter. But this part does, and this part does. So with every new loop of wire, you've doubled the length of the wire, right? Make sense? Good. Well, that's an electric motor. What's the opposite of a motor? A generator, right? A generator is the opposite of an electric motor. If electricity can produce magnetism, then why can't magnetism produce electricity? It can. Now, it's not quite as simple as electricity producing magnetism, because there's no conditions on that. If you have an electric current, it will produce magnetism every single time. If you have a magnetic field, it will not produce electricity every single time. There's conditions that are attached to that. Basically, you got to have motion. If you've got a magnetic field and you've got a wire, you can make a current. You can make electricity in that wire. But either the magnetic field or the wire has to be moving. Does that make sense? You got a wire just sitting there. You got a magnetic field just sitting there. Nothing happens. You got a wire and a magnetic field and you move the wire, then you're going to get a current produced in that wire. If you move the magnetic field, then you're going to get a current produced in that wire. That's how almost all electricity generation works. Not solar power, okay? But most electricity generation works by this generator effect, simply moving a wire relative to a magnetic field. Hydropower, big in Ontario, hydropower. How does it work? We get these big dams. Who's ever seen the Hoover Dam? Some of you guys have maybe driven over top of the Hoover Dam. Now there's a big bridge in front of the Hoover Dam, so you can't actually physically drive over top of the Hoover Dam. But it used to be that the Hoover Dam was the bridge across the Colorado River, and you drive over top of it. The Hoover Dam is massive. Okay. It dammed up the Colorado River and created this giant lake that they call Lake Mead that's behind this dam. What does it do? It keeps all that water with a lot of gravitational potential energy behind the dam. And as that water goes through the dam, okay, through these pipes basically in the dam, it gets moving fast. And as it gets moving fast, it gets to the bottom and it turns a turbine. The turbine is essentially a wire. It's a little bit more complicated than that, but essentially a wire in a magnetic field. When it moves that wire, when the water falling moves a wire that's in a magnetic field, what does it do to the wire? Produces an electric current in the wire. Okay, that's the electricity that comes out from it. Nuclear power is big in Ontario as well. Okay, we have no nuclear power in Alberta, but it's probably coming. How does nuclear power work? Everybody thinks, oh my goodness, it's so complicated. The nucleus does something and generates electricity somehow by the nucleus. Not exactly, no. The nucleus splits apart, and that's kind of a complicated process. But when it splits apart, it generates a lot of heat. What does that heat do? It doesn't generate electricity, it generates heat. That heat boils water. Literally, that's what it is. It boils water. Boiling water turns into steam. Steam rises. That rising steam turns a turbine, just like the falling water in the hydro dam turned a turbine. It's a wire moving relative to a magnetic field, produces electricity. Wind power that we have lots of down in southern Alberta. The wind comes, turns the fan, right? Turns the turbine. What is it? It's a wire moving through a magnetic field. As the wind pushes it, generates an electric current. When I was a kid, I've got a light for my bike now, so you can ride, when it's dark. But when I was a kid, the light for my bike was much more primitive than the lights that we have now for bikes. And you can buy a light for your bike now for, $10, $15. It's low power consumption LED lights, right? They don't take very much battery power at all. When I was a kid, you didn't even have lights with battery power because the batteries were so terrible and the lights were so terrible. The light for my bike when I was a kid was dependent upon me pedaling. Literally, it would generate electricity as you pedaled your bike. There was a little thing that rubbed up against the wheel. Okay, and when the wheel turned, this thing turned. And as this thing turned, it moved a wire through a magnetic field, generated an electric current, and powered my light. The downside of that was you had to pedal. Whenever you stopped, the light went off, right? Whereas lights now, obviously, they're battery powered, so that doesn't happen. Okay, so if electricity can generate magnetism, then magnetism can generate electricity. If either the wire or the magnets are moving, one of them's got to be moving relative to one another. If you take a look at the diagram that you see on the left-hand side here, this is going to explain to us why an electric current why a wire in a magnetic field will generate an electric current if the wire moves. Okay, let's look at the magnetic field here. Let's pretend that there's no magnetic force here. Let's pretend that there's no velocity. All we have is a magnetic field. We have a wire. We have electrons in that wire, but the electrons aren't moving. It's just a wire that carries no current in an external magnetic field. Now, let's move the wire. Let's push the wire, whether it's by pedaling my bike, or whether it's by water falling through a hydro dam, or whether it's by steam rising as a result of a nuclear power plant. Doesn't matter. Let's move the wire. Okay, I'm going to move the wire upwards. So now this wire has a velocity that's upwards. Okay, not caused by any kind of fancy magnetic or electrical effect. I pushed it. Okay, something pushed it upwards. That wire is moving upwards along with the electrons that are inside the wire. They're moving upwards as well. Doesn't matter how they got moving, they're moving. Let's do a hand rule on that wire, on that electron now. Okay, forget about the wire itself. Let's do a hand rule on the electron that's inside that wire, because it's moving through an external magnetic field. We're going to say thumb in the direction of the particle. The particle is moving upwards because I pushed it upwards. The fingers are in the direction of the field from north to south. Palm points which way? Outwards. So there's a magnetic force on that electron that pushes it out of the page. There's a magnetic force that pushes that electron and all other electrons there through the wire. What do you call that when an electron is pushed through a wire? It's a current. So we've just generated an electric current by a magnetic force. Does that make sense? So fundamentally, it still comes down to Ørsted's discovery, right? Electricity generates magnetism. It still comes down to that because we wouldn't have generated the electric current there. We wouldn't have generated the magnetic force on that electron if the electron, when it was moving through the magnetic field, didn't generate its own magnetic field. So a moving electron generates a magnetic field, interacts with the external magnetic field to produce a force on the electron that pushes it that way. In other words, to produce an electric current. Okay, if we hook that up to a circuit like you see over here on the right side, maybe you've got a light bulb over here, or maybe you've got an electric fan over there or something like that, and now it powers it. Make sense? All right, that's it for today, guys.